Okay, let's just start with our today's lecture. From the time we started our course of thermodynamics, in the very first lecture, we stated the fact that the main reason to study the course of thermodynamics is that we want to use energy, most of the energy available in the universe, on the planet, is in the form of heat, and that heat is many times or most of the times is useless form of energy. You cannot do anything out of it. So we need systems, we need to design, we need to devise systems that can convert heat energy into useful work output. So we need to convert this heat into useful output. So this is our this okay. So this is our main objective. So this is the main objective based on which we started. Now the thing is that in order to study this energy transformation process, we first went through the first law of thermodynamics. And the first law of thermodynamics is stated that energy can be transformed from one form to another form. And we actually devised equations for it. The fundamental, the main equation that we determined in chapter number 2 was about the first law of thermodynamics. Okay, and that equation actually tells that the energy can be transformed from one form to the other form. And the most important transformation for us is basically we have heat energy, G, Q, and we need to transform it into work output. Okay, so this is what we want. This is the main objective of thermodynamics. We want to convert heat into work output. Now, by the first law of thermodynamics, we develop an equation, and through the equation, we know that Q and W are interrelated in that equation, and we can use that equation to find out how much, to find out the conversion of heat energy into work. And then there are other forms of energy as well. There is pressure energy, there is energy, kinetic energy, so because of the velocity, there is potential energy because of the elevation. So there are other forms of energy. There is the energy of mass going in, mass going out. Anyways, the net thing is that we can relate all of these forms of energies with one another, and these energies are interchangeable, and this is the outcome of first law of thermodynamics. We applied the first law of thermodynamics to closed systems, and we developed the equations, we solved the problems for those closed systems in chapter number 4. Then we applied the first law of thermodynamics to open systems, and we developed the equations and we solved the problems for the open systems in chapter number 5. So basically, the conversion of one form of energy to another form is this subject is completely covered by the first law of thermodynamics. However, there are still some details missing. Those details are like, for example, okay, I know that if I have heat, I can convert it into work, but how much? How much of heat can be converted into work? Okay, is it possible to that if I have, let's say, 10 kilojoules of heat, can I convert all of that 10 kilojoule into 10 kilojoule of work? Is it possible? Now, this is a question which first law of thermodynamics does not explain. First law of thermodynamics does not put any limitation. It just tells that energy can be transformed from one form to another form, but it does not put any limitation. All those limitations are the qualitative issues, and these issues are actually handled by the second law of thermodynamics. The most common example you're going to see here is, let me show you here this one. Okay, you see here, suppose this is a container, and this container is filled with water, and then what you do is that you put a shaft inside the container. Okay, now when you rotate the shaft, so there is a work here. Okay, so the work done by the shaft, what will happen to it? It will cause certain friction between the water and the shaft. Some heat will be generated, and so some heat can be transferred out. Okay, so our work can be converted into Q. By just rotating the shaft, you can actually convert work into Q. But let's talk about the other way around. Let's say that I have a shaft here and I supply externally some heat to the water. Will it be possible that you convert this heat into work output? No, naturally this will not be possible. First law of thermodynamics says that W can be converted into Q. In the same way, Q can also be converted into W. First law of thermodynamics does not put any restriction. It just tells that energy can be transformed from one form to another form. But the second law of thermodynamics put a restriction. Second law of thermodynamics says that yes, you can convert work into heat here, but this is one-way process. You cannot convert heat into work. It's not possible that you just supply energy to the water and it will make the shaft start rotating. The shaft will not rotate even if you supply heat to the water. So this way is not possible. That way is possible. So there is a direction of transformation. So transformation of energy from W to Q here is possible naturally, but transformation of energy from Q to W is not possible. This thing was not explained by the first law. First law just says that yes, W and Q are interchangeable, intertransformable. So you have an equation, and through the equation you can convert W into Q or Q into W. But in reality, in practice, in the real world, the second law tells that no, there is a limitation. In one way, the process is possible. The other way, transformation and this process is not possible. Do you understand the specific difference between the first law and second law, and what areas the first law and second law deals?
Yes, sir.
Okay. So first law deals with the quantitative aspect. That yes, energy can be transferred from one form to the other form, but it does not put any limitations. Those limiting details are actually provided by the second law. And the second law of thermodynamics thus actually fulfills the first law. The gaps within the first law which were not actually completing the process details are being filled by the second law. So second law actually fills the gap which were not filled by the first law. Okay, second law provides the details, the qualitative aspect. Secondly, the first law of thermodynamics will tell you that if you supply, let's say if you supply work, then this work can be transformed into Q. But will all of the work can be transformed into Q? Will it be like 100% transformation, or is there any limitation to it as well? Okay, so what is the maximum amount of limit that can be transformed of energy from one form to another? That maximum limitation is also not mentioned by the first law. The second law explains the limit. Second law mentions limit. Okay, so if I have 10 kilojoule of work, can I convert all 10 kilojoule of work into 10 kilojoule of heat? The first law says yes, you can do it. But second law will put a limitation that no, out of this 10 kilojoule, this much amount you can convert and this much you cannot convert. Okay, so all these details which were not mentioned by the first law are the things which we are now going to cover in the second law of thermodynamics. So this is basically the introduction to the second law of thermodynamics. I have posted already some videos under the lecture material of chapter number 6 for the second law of thermodynamics. These were the YouTube videos, and I would like to request you to watch them. They are explaining the fundamentals, basis, ground of those laws which tends to produce the second law of thermodynamics, which becomes the basis to study the second law of thermodynamics. Okay, anyways, so here we're going to study second law of thermodynamics. So we're going to talk some new terminologies here about the reversible, irreversible processes. We're going to study the heat engine, refrigeration, and heat pumps on a holistic view. We're going to study about the temperature, Kelvin temperature scale, but this is not something of really of our concern. That's about the third law of thermodynamics. The third law of thermodynamics is not directly concerned with us right now. We're going to talk about the maximum thermal efficiency and the Carnot cycle. Okay, so introduction to second law. Not every processes are consistent with the principles of energy conservation. Just energy conservation, first law, cannot really explain all the processes. We need more information. We need to have the direction. Okay, heat transfers from high temperature to low temperature. Okay, there is always a direction of the process to work. Okay, that direction is explained by the second law, but not by the first law. Okay, so by the second law, there are many advantages of the second law. We actually develop the ideal theoretical performance of the engines, of the devices. Also, we are going to develop the temperature scale, but this is something which is not really directly linked with us. That's about the third law of thermodynamics. The second law of thermodynamics behaves as the basis for the development of the third law of thermodynamics, but third law of thermodynamics is not really of much concern with us. So we're not going to focus more on this. Okay, so now we have, before going to the next topic, I need to ask, is there anything which is not clear to anybody, any concept, anything you want to ask? Everything is clear so far?
Yes, sir.
Okay. Okay, now let's discuss about some new terminologies. They're simple, but anyways, they are going to be used here a lot. Okay, the first is thermal reservoir. Reservoir is basically what it is, a large body. Okay, and when we say thermal reservoir, it means a large energy containing body, or a large body containing energy. Okay, so that's a thermal energy reservoir or heat reservoir. Is a body with large thermal energy capacity that can supply or absorb finite amount of heat without undergoing any change in temperature. And this is something we can visualize it on a daily life. Okay, like for example, if I have a glass of hot water and I go to the sea or the ocean, and I put a glass of hot water into the ocean, will it change the temperature of the ocean? Of course not, because a glass of water is nothing compared to the size of the ocean. Even if you put one jug of hot water, still it's not going to change the temperature of the ocean at all. Okay, so temperature, the ocean is going to absorb all the energy without changing its temperature at all, and so the ocean behaves as a reservoir in this case. Similarly, outside air. Okay, let's say I throw some of the energy to outside air. Will it change the temperature of the outside air? Will the weather change just because I'm throwing some of the energy to the outside air? Of course not, because outside air is a very large body, and throwing a small amount of energy, minute amounts of heat is not going to affect at all or the overall temperature of the outside atmosphere. So the whole outside atmosphere behaves as a reservoir. Another example, let's say you see daily we receive the solar energy. The sun is giving us energy. Okay, so sun is supplying us energy. Since the sun is giving us energy, is the temperature of the sun changing because of that? Of course not, because the amount of energy the sun is giving is so small compared to the energy inside the sun that even after providing us that much amount of energy on daily basis, the temperature of the sun does not change. Okay, so the sun behaves as an energy reservoir. So from these examples, you can just simply understand what does a reservoir means. A reservoir can absorb energy, can supply energy, but in a way that its temperature is not going to change, because those finite amounts are so small compared to the total big size of the reservoir that it's not going to have any effect over the temperature of the reservoir itself. Do you understand the concept of the reservoir or not?
Yes, sir. Yes.
Okay. Now, within the reservoir concept, we have two further subclassifications. One is known as the source, the other is known as the sink. Source is basically what? It is a reservoir which is supplying energy, but given the definition that it supplies energy, but while it is supplying energy, that does not affect the temperature of the source itself. Similarly, sink is a reservoir that absorbs energy, but given the fact that although the sink absorbs energy, but it does not change the temperature of the sink at all. So while absorbing energy, still the overall temperature of the sink remains the same. Okay, so source is an energy is a energy supplying reservoir, and sink is an energy accepting or energy absorbing reservoir. Do you understand the difference between the source and the sink?
So, sir, the sink is like the ocean.
Yes.
Where,
Yes.
the example you gave.
Yes. The ocean
Okay.
is the sink. Outside air is also sink. Okay. Outside atmosphere is also sink. If it is if you are rejecting heat to it, okay, then it is sink. Suppose you are in summer, okay, and now the outside air temperature is very high, okay, and the heat is now coming from outside to your room or to your body. You go and you are receiving heat from the outside air. So then the outside air is going to behave as a source, because it is now giving you the heat, but its temperature itself is not changing. Okay, so just understand it by the definition. Anything which is supplying heat is a source. Anything which is accepting heat is a sink. But given the fact that the temperature of the source and the sink does not change because of the supply or the absorption of the heat. It's clear?
Yes.
Okay. Okay, so heat transfer is the only interaction between thermal reservoir and its surroundings. Reservoir temperature remains uniform and constant during the process. Okay, heat transfer only results in a change in the internal energy of the reservoir. Okay, anyways, so you already got the concept here. Let's move over to the next topic, reversible and irreversible processes. Now, reversible is something that can be reversed. Okay, let me give you an example. I have a glass of water. It is in the form of water. I put it into the fridge, and then this water is converted into ice. Okay, a process has occurred. Liquid converted into solid. Now I take the glass of water back, put it outside. After some time, the ice converts back into liquid. Okay, so now the reverse has occurred. So a process went in one direction, liquid converting into solid, water converting to ice, and then the process reverts back into the other direction, where ice converted back into water. So this is a reversible process. A process that can be reversed is a reversible process. Is it understandable?
Yes.
Okay, now let me give you an example of an irreversible process. Okay, suppose I rub my hands together. Okay, so when I'm rubbing the hands, I'm using the mechanical energy of my body. And what will be the effect? When the hands rub against each other, so there will be friction, there will be heat generated. Okay, so what's happening is that I'm converting mechanical energy into heat energy. Okay, now this is one process. One process has occurred. Mechanical energy converted into heat energy. Now somehow, let's say if I heat my hand, can that heat be converted back into mechanical energy? That will not be possible. Okay, so this is an irreversible process. You can convert the mechanical energy of your hand to heat, but then this heat will be lost, and first of all, you cannot catch that heat back. And even let's say if you are able to catch that heat back, you cannot convert that heat back into the mechanical energy. Okay, so this is an irreversible process. Okay, so do you understand the irreversible process?
Say, yes.
Okay, so now here in thermodynamics, the scientists have devised a very unique methodology of defining the reversible and irreversible processes. What do the scientists say is that all processes are reversible process, except that there are certain irreversibilities. If any of those irreversibilities are present in a process, this will make the process irreversible. So a process without irreversibilities is a reversible process. But if any of the irreversibilities are there, then these irreversibilities will make the process irreversible. I'm not sure if I confused you or not, okay? Now, the scientist says that there are certain type of irreversibilities. For example, friction. Friction is an irreversibility. Why? Because friction generates heat, but that heat cannot be returned back. Normally, whenever the heat is generated because of the friction, that heat is lost. You cannot get that back. You cannot get back that heat, okay? So friction is an irreversibility. If there is any system in the world where it has friction, then this is an irreversible system, because friction, the heat lost by the friction cannot be returned back. This is one example. There are about more than 10 different kind of irreversibilities. Okay, viscosity. Viscosity is also kind of a friction between the layers of the liquid. So if you have liquid have multiple layers, and there is viscosity between those layers. So if a liquid has viscosity in it, then this is an irreversibility. It's going to generate heat, and that heat will be lost, can never be returned back. Okay, so this is another example. Okay, so there are multiple irreversibilities. We are not going to go into the details of that, but I just want you to grasp the general idea. What is the difference between the reversible and irreversible processes? Reversible processes are the ones which has no irreversibilities. But if any of the irreversibility come into it, that will make a reversible and irreversible process. And there are different kind of irreversibilities. Friction is one example. Viscosity is another example. Finite temperature difference is another example. Okay, there are different kind of irreversibilities there. We are not going to study those irreversibilities, but you just want to know the difference between the reversible and irreversible processes. So far, everything is okay?
Yes.
Okay. Now, when we say irreversible and irreversible processes, actually reversible is an ideal process, because in reality, in the world, we have irreversibilities. All the time we have irreversibility. Okay, I gave you a very crude example of liquid converting into ice and ice converting back into liquid, but there are some irreversibilities into this process as well, which I did not mention to you. Okay, the reason behind the fact that you won't be able to understand it at this moment, but I just wanted to give you an idea. Okay, so there are so many irreversibilities in the world that nothing is ideal. The world is actual, nothing is ideal. Okay, so anyways, so the point is that irreversibilities make a process irreversible, and in the world most of the processes are irreversible. Okay, so whenever we want to say something ideal, we say reversible. Reversible means something which has no irreversibilities. Because of irreversibilities, most of the time what happens, you have losses. So when you say that a process is reversible, that means you, in another way, you are saying that there are no losses in the system. No losses in the system means this is an ideal system. Okay, so just try to equate these things together. Okay, many times you will find, okay, this is an ideal cycle. An ideal cycle means what? Means a cycle with no irreversibility. Means a cycle with no wastage. So these things should come to your mind directly. Just link these things together. No wastage, okay, means reversible, means ideal. Okay, and whenever there is irreversibilities, that means it is actual. That means there are wastage. Okay, that means it's not 100%. Okay, so these things are all interlinked together, connected. These words which I'm saying. Okay, so these things should come into your mind. An irreversible process is when the system and all parts of its surrounding cannot be exactly restored to its respective initial states after the process has occurred. Okay, irreversibilities may be found within the system and within its surroundings. There could be internal irreversibilities, there could be external irreversibilities. Again, our topic is not about to study the irreversibilities. The whole idea was to just differentiate you between the ideal and the actual processes, the reversible and the irreversible processes, and what is the relationship between them. Okay. Thermodynamic cycle. Thermodynamic cycle means a cycle which is a closed system. It starts from one state point, follow multiple processes, let's say from 1 to 2, 2 to 3, 3 to 4, but return back to its original state. Okay, so this is a thermodynamic cycle. Okay, there is a big definition written here, but anyways, you can go through the definition. Definition is correct, but I don't need to explain it to you. The simple explanation is many times more easy. Okay, so thermodynamic cycle means a cycle which starts from one state point and return back to the same state point after passing through multiple processes. Okay. Okay, so next thing is the statement of second law. First of all, there are two statements of second law, and one statement is known as the Kelvin-Planck statement. The other statement is known as the Clausius statement, and both statements are very important. Okay, so we are going to study both the statements. Okay, so let's first discuss about the statement number 1 of the second law. It is known as Kelvin-Planck statement of the second law. Okay. You see here, I have prepared a summary. You can say this is a summary sheet for all the devices that we are going to study in this chapter, and I have just summarized them together on one page, so it's going to give you a good picture so you understand everything very well. Okay, so before going towards this Kelvin-Planck statement or the Clausius statement, let's first discuss about 3 different devices that we are going to study in this chapter today. The first thing is a heat engine. Okay, what is a heat engine? The heat engine is a device. Main objective of a heat engine is to produce power. That was the main idea of starting thermodynamics. We have a lot of wastage heat, useless heat, and we need to convert it into useful output. The useful output, one of the most useful output is the power. So if we can produce power in any of the form, we are not discussing which form of power we are talking about, but anyways, if we produce the work output as power from the heat, this is heat engine. So heat engine is basically a device. It's a system which uses heat to produce power. Okay, this is first thing that we are going to study. Then we have another thing, which is refrigerator. In case of refrigerator, it is a device, but the main objective of the refrigerator is not to produce power. We do not produce electricity from refrigerator. Okay, the main objective of refrigerator is to produce cold. Okay, so this is the second device which we are going to study today. Okay, then we have a third device, which is heat pump. Heat pump is simply something which you are not very well aware of most of the time because you live in Karachi or the hotter parts of the world. So those who lives in the cold areas, they are more familiar with this heat pump. Heat pump is like inverse of AC, because for the AC it produces the cold and provides you with the cold environment. Heat pump is something that produces hot, produce heat. Okay, so it produces the hot environment, and most of the time it is needed in the winter area, in the winter season, in the cold areas. Okay, where you have a lot of cold environment, and you need to produce heat to keep yourself warm. So heat pump is a device that produces heat. Okay, so these are the 3 devices that we are going to study today, and you need to understand against each name there is an objective. Whenever it is heat engine, the objective is to produce power. Whenever it is refrigerator, the objective is to produce cold. Whenever it is heat pump, the objective is to produce heat. So far, are you with me? Is everything clear so far?
Yes, sir. Yes. Yeah.
Now, the thing is that we are not going to study any of the device itself, the details of the device we are not going to study in this chapter. Heat engine, we are going to study in chapter number 9 and 10. The details of it, what are the components of it, how does it produce power, okay? What are the processes that occur inside? We are not going to go into that detail in this chapter, okay? So we are not going to study the details of the heat engine in this chapter. Heat engines, we're going to study in chapter number 9 and 10. Refrigerator. Refrigerator is something that, again, refrigerator and heat pump, we are not going to go into the details of it. We are not going to see what are the components of refrigerator and heat pump. We're not going to see what are the processes that occurs in them right now. The only thing we're going to see is the holistic picture. What goes in, what goes out. That's it. We're going to see. We're not going to go into the details of it. For refrigerator and heat pump, we are going to study this in chapter number 11. Chapter number 11 is the chapter where we are going to study both heat pump and refrigerator. Okay, so let's talk about the holistic picture of heat engine. What is heat engine? Okay, so first of all, heat engine is a device, okay, which takes in heat. So you have heat, you supply heat to this device. Okay, now right now we are going to represent the heat engine like a circle with a cross inside. It doesn't mean that it looks like this. In reality, it's entirely different. We are going to study it in detail in chapter 9 and 10, how it looks like. But right now, just as a symbol, we're going to represent it like this. There's a cross circle and a cross inside, okay? Similarly, the refrigerator and heat pump, we are not going to go into the details of these devices right now. But just we are going to represent them as a circle and a cross, okay? So the thing is that you have a heat engine, and we supply heat to the heat engine. Okay, so heat goes to the heat engine. Okay, and then what happens is that let's say this is our heat engine. Okay, and then what happens is that some of the work is produced, workout. Okay, and this was the main objective of the heat engine, to produce power. This power is your workout. Okay, now here comes the Kelvin-Planck statement. Now, what does the Kelvin-Planck statement says? So let's go back to the Kelvin-Planck statement. Okay. The Kelvin-Planck statement says it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surrounding while receiving energy by heat from a single reservoir. That means that this is our heat engine, and heat is being supplied to the heat engine, and it is impossible to convert all of this heat to work. That means if you want to convert heat to work, the second law of thermodynamics put a limitation that part of it will be converted to work, and there must be some wastage. So there will be some part of the heat that will be wasted out. So this is the second law of thermodynamics, Kelvin-Planck statement. You supply heat, and if you think that you can convert all of that heat to work, then you are wrong. It's not possible. This is the real world. You will have wastage. You cannot have a system without wastage. This is second law. Second law placed a limitation. First law say that yes, you can convert Q to W. And first law might say that you can convert all of the Q to W. But second law says no, you cannot convert all of the Q to W. You can convert part of it to W, but there will be some part of the Q which will not be converted to W and will actually be wasted. This is what the second law says. Are you making a connection between the first law and second law here?
Yes, sir.
Okay. So Kelvin-Planck statement, it says it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work. Net amount of energy by work to its surrounding while receiving energy by a single heat transfer from a single thermal reservoir. So you're receiving heat from a single thermal reservoir and you're converting all of it to work. This is not possible. So the statement is, it is impossible. Okay. So this is the first law of thermodynamics. This is the second law of thermodynamics, Kelvin-Planck statement. And so let's go back to our summary page. If you look here, this is a heat engine. So it says that you have the heat engine. The heat engine is going to get heat from, obviously, when it is getting heat from something, so that will be the source. So we call this heat source. Heat source or hot reservoir, they means the same thing, okay? Because they're supplying heat. And obviously, it will be at high temperature. So you can say TH. TH could be high temperature. You can call TH as heat source temperature, hot reservoir temperature. All mean the same thing. And it's going to supply the energy. Okay, this energy is going into the heat engine. This is my heat engine. This is going into the heat engine. So obviously, this is my input. So I can call it Q in, or I can call it QH. Okay, QH also means the heat coming from the hot reservoir or the heat source to the heat engine. Okay, then there will be some work output from this heat engine, and this will be my main output. Okay, but as per the Kelvin-Planck statement, as I told you, this heat engine works over the Kelvin-Planck statement. So as per the Kelvin-Planck statement, it says that this is must. You will have some wastage. Okay, so the wastage will be what? It will be the amount of heat going out, rejected by the heat engine. You can call it QC, because when the heat will be going out, it will go to some reservoir. It is coming from a reservoir, it's going to go to the reservoir. Okay, so it should be a cold reservoir comparatively, obviously. So you can call it QC, you can call it QL, you can call it Q out. Why I have written all the three names here? Because in the book, sometimes they use it interchangeably. Sometimes they write it as QC, sometimes they write QL, sometimes they write Q out. Anyways, whatever they write, they mean all the same thing. So this is the cold reservoir, it's a heat sink, okay, and it will be at a low temperature. So you can call it TL or TC, okay? And so this is how the heat engine works, okay? So it takes heat from the hot reservoir and converts part of it into work output, and the remaining is rejected to the cold reservoir, okay? So in terms of the heat, Q in or QH goes in, work out goes out, as well as QC and or QL or Q out goes as rejected. So that means this is not possible, Q going directly to the work output. There will be some. So you will have Q in here, and there should be some Q out. This is Kelvin-Planck statement. Do you understand do you understand how Kelvin-Planck statement is defining a heat engine?
Yes, sir, yes. It makes sense.
Okay. Now let's talk about the efficiency. What is the efficiency? Efficiency is output over input. It's a simple definition of efficiency you have studied many times before. It's output over input, okay? So in case of this heat engine, so our output is what? Our output is our objective. Our output is basically here the workout, because this is our main objective. So this is our output. So it's going to come here. And what is our input? Input is the energy we are putting it into the heat engine. So this is our input. So it's going to come here. Okay. So we have W out minus W out divided by Q in. Now from here, you can simply see there is a relationship between W out, Q in, and Q out. Okay. You can simply see the relationship here. So Q in is equals to W out plus Q out. So that means W out is equals to Q in minus Q out. Okay. Do you get it? Q in, if you look at the arrows, Q in is equals to W out plus Q out. So W out basically becomes what? Q in minus Q out. So I can just simply write here, instead of W out, I can write here Q in minus Q out. Or I can write here the efficiency as 1 minus Q out over Q in. So this becomes the efficiency of my heat engine. Do you understand this definition here? All the formulas so far?
Yes, yes, sir.
Okay, good. There's the last formula written here, but let's not discuss it now. We're going to discuss this one later. Okay, let's go back. Here was the Kelvin-Planck statement. I've discussed the Kelvin-Planck statement in detail with you. Okay, then we have this is a heat engine. I discussed what is a heat engine with you. Okay, discuss about the thermal efficiency, discuss this diagram with you, discuss these formulas with you. So all of these things are already discussed with you now. Okay, now the next is the second statement. Now the second statement of the second law of thermodynamics is the Clausius statement. Okay, now let's discuss about what this statement is. The Clausius statement, actually, Clausius was an intelligent person. Okay, he was an intelligent person. What he did was that he looked at it very carefully, the heat engine. Okay, if you look at it carefully, you're going to see this thing, that the heat is being transferred from high temperature to low temperature. The heat is being transferred from high to low temperature, and this is the nature. When the heat is transferred from high to low temperature, in the process, you can get some work output. So what he realized is that if this is possible, the reverse should also be possible. Okay. Instead of getting work output, let us say if we supply work input, then we should be able to move the heat in the opposite direction. So generally heat moves from high temperature to low temperature, but if we supply some work input, then we should be able to move the heat from low temperature to high temperature in the opposite direction. Okay, so this becomes our Clausius statement. Okay, so basically Clausius statement was what? Let me go to the Clausius statement. Okay, so the Clausius statement is that it is impossible for any system to operate in a device in a way that the sole result would be an energy transfer by heat transfer from a cooler body to a hotter body. Remember, heat always transfers from hot to the cold. This is possible naturally. Naturally, this is not possible. This is the Clausius statement. But if you are able to supply some work input, if we are able to supply some work input, then this becomes also possible. So this is the Clausius statement. It is impossible if you do not supply any work in. The sole result is this, heat moving from cold to hot. It's not possible. But yes, if you supply work input, this is possible. And this is in reality what's happening. Just try to imagine what's happening with your AC. Your AC is producing cold inside the room. Okay, so the room is at cold temperature and outside is at hot temperature, and the AC is taking heat from the room and throwing it outside. So basically, AC is taking heat from the cold body and throwing it to the hot body. This is not possible until and unless you supply some work input. And yes, we do supply the work input. The kind of work input that we supply is in the form of electrical energy. You connect the AC to the electrical socket, and then once you connect the once you connect the AC to the electrical socket and the electricity is supplied to the AC, it's the electrical work which is the work input, and that results in the transfer of energy from the cold body to the hot body. The against nature. Nature always says that heat transfer from hot to cold, but here you are transferring heat from cold to hot. How you are doing it? By supplying work input. And this is according to the Clausius statement. This is possible only if you supply the work input. So Clausius' statement of second law is that it is impossible for any system to operate any device in such a way that the sole result would be an energy transfer by energy transfer from a cooler body to a hotter body. That is not possible. But yeah, if you give work input, then it is possible. So anyways, these statements were written in a really difficult way that if you are not if you're not a good knowledgeable person, you cannot really you can hardly understand these statements. But anyways, I've tried my best to explain you. Are these statements making sense to you now?
Yes, sir.
Okay, so this is the Clausius statement. So now let's study our refrigerator and the heat pump, the Clausius statement. Okay, so let's talk about refrigerator. So first of all, refrigerator works in an opposite way as that of the heat engine. Okay, so in the heat engine, we had the work output. Here, instead of work output, we have work input. In the heat engine, the heat flows from high temperature to low temperature, but here we are making the heat to flow from low temperature to high temperature. Okay, so we are moving in exactly the opposite way as that of the heat engine. So we have work input here, it goes into our refrigerator, and then this allows the heat to move in the opposite direction. So heat moves from the cold reservoir, okay, so QC or QL, okay, and it goes into the hot reservoir. Okay, so hot reservoir is at temperature TH, cold reservoir is at temperature TC or TL, okay, and QH is the amount of heat rejected here, you can say. So input plus QC, they are going to combine together and it's going to go as QH into the hot reservoir. Most of the time, in case of the refrigerator, our cold reservoir is our cold space. Okay, if you're talking about a fridge, that's a cold space inside the fridge. If you're talking about the freezer, that's a cold space inside the freezer. If you're talking about AC, so this is our room. This is the cold space that we want to generate. Okay, so most of the time, this is the cold space, and since this is our main output, why? Because this is our main objective. Our main objective of the refrigerator is to produce cold. So this is our main output. Input is definitely the electrical input that we supply. Whether if it is a refrigerator or an AC, you need to connect into electrical socket. And so obviously you are providing energy and you are paying for the energy. Okay, so if you're going to use electricity, you're going to pay the electrical bill. Okay, so anyways, so this is the main idea. So this is how the refrigerator works. Okay, the efficiency of the refrigerator, we don't call it efficiency, although it is efficiency, but we give it a new name. We call it coefficient of performance. The reason of why we call it coefficient of performance is that efficiency cannot be more than 100%. But from the setup of finding the efficiency of refrigerator, the value can become more than 100%. Since the value can become more than 100%, so it is the efficiency, but let's give it a new name. Let's not call it efficiency. So we call it coefficient of performance. If you just look at the name of this coefficient of performance, it actually means efficiency. But why we are not calling it efficiency? Because its value can be higher than 100%. And efficiency is something that we know universally, it should not be greater than 100%. So anyways, we call it coefficient of performance. It's always output over input. The output in this case is basically the cold space, the amount of heat extracted from the cold space. So it's QL or QC. Input is W in. Okay, this is the electrical input that we supply. Okay, from here you can see that QC plus W in together makes QH. It's written here W in plus QL equals to QH, or I can write here W in equals to QL minus QH. I can replace the value of W in from here like this. The coefficient of performance of the refrigerator becomes QL over QH minus QL. Do you understand this formula? Is this clear or not?
Yes, sir.
Okay, the next thing or the last thing is basically heat pump. Heat pump also behaves as the same way as refrigerator. There is only one slight difference. The difference is that in case of the refrigerator, our main objective was to produce cold, so our output was QC. Here, our main output is not to produce cold, but in case of the heat pump, our main output is to produce heat. So our output is actually QH. That's the only difference. Otherwise, it works the same way as the case of the refrigerator. No difference. The only difference is in the COP, because in the COP you have output over input, but in case of refrigerator, our output is to produce cold, so it's QC. In case of heat pump, our output is not this. Our output is our main objective is to produce produce heat. So that will be QH. So it will be output over input. So instead of having QL over WN, it will be QH over WN. That's the only difference. So WN will be the same, QH minus QL, and now our COP will be QH over QH minus QL. You look here, the COP was QL over QH minus QH. The only difference is here it was QL, here it is QH. Okay, this is the only difference. Otherwise, this becomes the formula for coefficient of performance for the heat pump. Refrigerator and heat pump, they behave based on the Clausius statement. Heat engine works over the Kelvin-Planck statement. And I have mentioned you all the formulas and the figures, okay, except for the last three formulas here. For each one, there is a last formula, which I have not explained to you right now. I'm going to explain you later, okay. So in this formula sheet, except for the last three formulas, is there anything which is not clear to anybody? Please ask. Everything is okay? Are you catching up with me?
Yes, sir.
Okay. So I have explained you this Clausius statement. I have explained you what is the refrigerator and heat pump. I have explained you this figure. I have explained you the objective of refrigerator, the objective of heat pump. I have explained you the COP values for heat pump and refrigerator. Next is the example. So let's have a break of 5 minutes, and after that we can start our numerical. Anybody want to ask anything, you can ask. Okay, please put your attendance in the comment box. Please put your attendance in the comment box. Okay, so let's have a break of 5 minutes, and after that, inshallah, we'll be back. Assalamu alaikum, students. Can you hear me?
Yes, sir, we can hear you.
Okay, so let's study some of the numericals from this chapter. Okay, so we have a steam power plant. So first of all, it's a power plant. Power plant means something that generates power. So it's a heat engine. So we have a steam power plant produces 50 megawatt of net work. So this is the work output that it generates. While burning fuel to produce 150 megawatt of heat energy. Okay, so this is the heat energy which is actually supplied. They supply the heat energy by burning fuel. So this is basically Q in, or you can say QH, okay, at a high temperature. Determine the cycle thermal efficiency. We need to find what is the cycle thermal efficiency and the heat rejected by the cycle to the surroundings. So heat rejected will be the wasted heat. So that will be QL, or you can say it is QC or QL, both are okay. So first of all, by the definition, we have thermal efficiency is equals to W cycle over QH. Okay, we already saw this in our formulas. Okay, so thermal efficiency is W out over Q in, or Q in is the same as QH. Okay, so let's go back to our problem. So we have W out or W cycle, it's the same thing, over QH. So we're going to get what is the efficiency. And then let's talk about W cycle or W out. So this is equals to QH minus QL. And since we know what is QH and we know what is W out, so we can find what is QL. That's it. Is there anything which is not clear in the solution of this problem?
So sorry, my internet has been making some problems. Could you just repeat what QH and QL stands for?
Okay, let's go back. This is a heat engine. QH stands for the amount of heat supplied by the hot reservoir. In this case, we are doing it by burning fuel. Okay, so heat supplied by the hot reservoir, that's QH, or also QN, they mean the same thing. And QC, QL, or Qout, they all mean the same thing. It means the heat rejected by the heat engine. Normally, this heat rejection is to the heat sinks, and for most of the time, heat engine, the heat sink is the outside atmosphere.
Okay, I get it. Thank
Okay.
you.
Okay, so go back. Is there anything else which is not clear in the solution of this problem? Okay, let's move forward.
It's clear.
Okay, let's move forward to the next problem. Okay, we have a residential heat pump. So first of all, it's not a heat engine, it's a heat pump. The residential heat pump is used to provide heating during the winter season to maintain a house temperature at 21 degrees centigrade. So this is the temperature that needs to be maintained inside the house. So this is the TH. Okay, this is TH, which needs to be maintained inside the house. It's a hot. This is a hot reservoir temperature because this is a heat pump. In case of the heat pump, heat is supplied to. If you go back here in the case of slide, so you see for the case of heat pump, this is our output, and heat is supplied to the hot reservoir. Okay, so TH. This is our TH, and most of the time this is the heated space. This is the space that needs to be heated. Okay. Here we have TH. On a typical day, the heat transfer to the house is 75 megajoule per hour. So this is probably the QH. Okay, when the outside temperature, air temperature is -4 degrees centigrade, so this is probably TL. The heat pump has a COP of 3.7, so COP is given. Determine the power required for the heat pump. Power required for the heat pump will be W in or W cycle. And the heat transfer rate from the outside air. So this is basically QH, sorry, QL. That needs to be asked. So here again, we have the formula for COP of the heat pump. It is QH over W cycle. So we know what is COP, we know what is QH, so we can find what is W cycle. And then W cycle is QH minus QL. And then so from here, since we know W cycle, we know QH, we can find what is QL. Is there anything which is not clear?
Clear.
Okay. By the way, keep that in mind that these are all the conceptual things. The heat engine, refrigerator, heat pump, okay, and these are the formulas of their efficiencies. The efficiency of the heat engine, coefficient of performance efficiency is for the refrigerator is this one, and this is this one, okay? But there are alternate formulas for it as well. We come up to this formula from this formula. Similarly, we come up to this formula from this formula. Similarly, we come up to this formula from this formula. So you need to know all these formulas and the way we came up from one step to the other step, so that you can know how to solve the problems. Okay, let's go to the next example. Okay, so we have a heat pump. Again, this is a heat pump. Okay, so this is a heat pump with a COP, coefficient of performance, of 2.5. So COP is given. It supplies energy to a room at a rate of 63,300 kilojoule per hour. So this is the energy supply. Energy supply to the room. For the case of heat pump, when you are supplying energy to the room, that will be QH. Okay. Determine the electrical power input to the heat pump. So we need to determine what is the electrical power input. So electrical power input will be W in or W cycle. But we need it in kilowatts. So the better thing would be to convert initially this 63,300 from kilojoule per hour into kilowatt. And then finally find out the rate of heat absorption from the outside air. So this will be QL from this heat pump. So you can see the solution done here. So first of all, this is my own handwritten solutions. First of all, if you look here, in these kind of problems of chapter number 6, always you need to draw these diagrams. I mean, drawing these diagrams is a must. Because in these diagrams, first of all, you're going to draw the heat pump, then you're going to show where is the low temperature reservoir, you're going to show where is the high temperature reservoir. You will, for example, in this case, the high temperature reservoir is a room, the low temperature reservoir is the outside air. You're going to show where is the amount of heat transfer QH going to the room. This is the output, which one is the output, which one is the input. Okay, so you're going to show all these things. You're going to mention that how much is the work input, so W in, where it is coming in. Okay, what is QL? Okay, how much is the heat taken from the outside air? Okay, so this is going to give you this is going to provide an excellent picture of how the energy is moving from one reservoir to the other reservoir while passing through your device. Okay, where is your input? Where is your output? Where is the high temperature reservoir? Where is the low temperature reservoir? What are the temperatures? Here the temperature is not mentioned, but you also need to mention the high temperature reservoir. What is TH? You also need to mention what is TL. This is important. Okay, you need to draw these diagrams for these kind of questions. Okay, but once you have drawn the diagram properly, then solving the problem is very simple. There is nothing to it. Okay, the only thing is in the drawing the diagram. Once you draw the diagram properly, then it's very easy, because then you can simply know where is the output, where is the input. Okay, so here COP is given. Okay, so QH is given. You can convert QH from kilojoule per hour to kilowatt. Just need to divide by 3600, converting hour into second. For the heat pump, you know that COP is output over input, so you know where is output, you know where is input, you can find what is W in. Then for the heat pump, you know that QH is equals to QL plus W in. It's always W in is equals to QH minus QL. Whether it's W in or W out, it's QH minus QL. So from here, you can find what is QL. So this is the solution of this problem. Is there anything within the solution which is not clear? Please ask.
Yes, sir, we understand. Sir, I want to ask a question.
Mm-hmm.
Do you want us to derive these power efficiencies by ourselves by looking at the diagram or making a diagram?
No, 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 no. I don't want you to drive these formulas, but I want you to understand them in all their formats. Okay. The thing is that in the book they confuse the students a lot many times because sometimes they're using QH, sometimes they're using QIN, sometimes they're using QL, sometimes they're using QC, sometimes they're using Q out. I mean, these things confuse the students a lot. So you should be able to have a holistic picture of how things are happening in these figures. Okay. So if you have the good picture, you know, I don't want you to drive these formulas. You can directly utilize them from where it is.
So there wouldn't be a situation where you don't tell us if it's a heat engine or a refrigerator.
No, 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 no. It will always be told that whether it is a
Okay.
heat engine or it is a refrigerator or it is a whatever it is.
Okay.
Yeah. Okay, so let's see this problem. Okay, before going to this problem, let me introduce you to the concept of Carnot efficiency. Okay, Carnot efficiency, Carnot efficiency. Okay, so basically, explaining you the Carnot efficiency, I'm going to give you an example. Okay, let's say you want to purchase something. You go to the market and the market guy tell you that this thing is 500 rupees. So how would you decide whether it is cheap, whether it is expensive? You need a reference point. So the reference point most of the time is the production cost. So suppose the thing that you're about to buy has a production cost of about like 450 rupees or 400 rupees, and the person is selling you at about 500 rupees. So you can say that, okay, the price is okay, it's good. But suppose the same object, you know that the production price of it is 1 rupee, and the person is selling you at 500 rupees. So you know that this is too expensive, because you always compare something with the reference point. So if you know a specific reference point, so based on the reference point, you can make a judgment if something is cheap or something is expensive, if something is good or something is bad, if something is working fine or something is not working fine. Okay, if you don't have a reference point, you will never be able to know. Okay, so this is the main idea of Carnot efficiency. Basically, Carnot was a guy who devised, or you can say who predicted, or a specific cycle, thermodynamic cycle, which was an ideal cycle. It was a cycle which has no irreversibilities. It was a cycle which was, since there were no irreversibilities, but that means there were no losses in the cycle. So for that cycle, he designed that, okay, what will be the efficiency of that cycle? Okay, and that efficiency of that cycle is known as the Carnot efficiency. And now Carnot efficiency becomes the reference point to analyze all different kind of thermodynamic cycles in the world. Okay, so suppose you have any specific cycle, any thermodynamic cycle, and if you want to know that how good your cycle is working, so first you need to know that if suppose this was a Carnot cycle, it has no irreversibilities, it was an ideal cycle, what would be its efficiency then? And then you compare the efficiency of your actual cycle with the Carnot cycle efficiency. So based on that, how close or how far away the efficiency of your cycle with the Carnot cycle efficiency, you can make a decision that, okay, is your cycle performing good, or is your system performing good or bad? Okay, so that's the main idea. So Carnot efficiency is the ideal efficiency, is the maximum possible efficiency, is an efficiency for a reversible system, is an efficiency for a system with no losses. So this is a kind of an efficiency which becomes the reference point for you to analyze and judge the efficiency of any other cycle in the world. So Carnot, why it's given the name Carnot? Because Carnot was the guy who first came out with this cycle. We're going to study this cycle in a brief today by the end of today. But anyways, this was a cycle which has no irreversibilities. It is composed of all the ideal processes. And so there are no wastages. There are no losses in the cycle. And so the efficiency of the cycle was like maximum possible. In fact, not possible. Where was the maximum efficiency? Okay, so what we do is that we compare all the efficiency of our different systems with the Carnot efficiency. And Carnot efficiency, by nature, by law, we know that it is not achievable, it is ideal. Okay, but we always compare. This gives us a good reference point. Okay, and this gives us a limitation that, okay, this is the limit. Whatever be the efficiency of the Carnot cycle, this is the limit. We know that we cannot even achieve the limit, but this is the limit. Okay, so it gives us a good reference point. Do you understand the idea and the concept of Carnot efficiency here?
Yes. So we're just comparing the an ideal version of the cycle with the actual.
Yes, exactly. Yes. We are just comparing the ideal version of the cycle. Suppose if this cycle was ideal, had no irreversibility, then what would be its efficiency? Suppose your system is working at 30% efficiency, but now you want to see that, okay, 30% is good or bad. So let's see that if our system had no irreversibility, it was an ideal system, then what would be its efficiency? So suppose its efficiency is, for the Carnot efficiency of your system will be 40%, and your system is working at 30%, so it's good. Okay, but suppose let's say the efficiency of your system is 60%, but the Carnot efficiency is 97%, so it's not good. Okay, so always we need to have a reference point. So this provides us a good reference point. Okay, now how did it happen? Basically, this also became one of the fundamental reasons to go through the development of the third law of thermodynamics, and eventually the Carnot's efficiency was realized that if we just replace the Q's in the formula with temperatures, then it will become the Carnot efficiency. Okay, now how do we come up with this thing? There is a lot theory behind it, and we don't really have that much time to go through into it. Okay, so if you want, you can go. Everything is written in the book.
So what did
you
you say? Could you repeat?
Okay, so if we just replace Q in the formula of efficiency with temperature, but the temperature should be absolute, means in Kelvin. Okay, so if we just replace the Q's in the formula with temperature, then the efficiency, this efficiency will be known as the Carnot efficiency, ideal efficiency, maximum efficiency, reversible efficiency. So for the case of reversible heating, for the case of actual heat engine, the formula of efficiency is 1 minus Q out over Q in. But if we want to know that what is the ideal maximum reversible Carnot efficiency of the heat engine, so it will be 1 minus T out minus T out divided by T in. Is it clear? But the temperature should be in Kelvin. But the temperature should be in Kelvin. Okay. Now I'm using some terminologies here. Just try to catch up with me, because these terminologies are used interchangeably. Okay. If it is said that find out the maximum possible efficiency, So maximum possible is only possible when there are no losses. That means maximum possible is also the same thing as the reversible. That means reversible and maximum possible is also the same thing as the Carnot efficiency. Okay, so whether it is said find the Carnot efficiency, whether it is said find the reversible heat engine efficiency, whether it is said find out the maximum possible efficiency, whether it is said that find out the efficiency of the ideal cycle, they all mean the same thing. Okay, so don't just get confused at what is asked, what is not asked. These all interchangeably they are used. They mean the same thing. Ideal, reversible, maximum possible, Carnot. Four things I have mentioned here. Okay. In the similar way, as the COP for the refrigerator is QL over QH minus QL, but I can write here as TL over TH minus TL, and this is going to give me the refrigerator's efficiency, COP, but that will be reversible, Carnot, ideal, maximum possible. Similarly, for the case of heat pump, this was for the refrigerator. Similarly, for the case of heat pump, the formula is QH over QH minus QL. So if I want to know the reversible, maximum, Carnot, ideal efficiency of the heat pump, that will be TH over TH minus TL. Is this thing clear or not?
Yes, sir, it's there.
So now if you look here on this formula sheet, there is nothing in it which is not clear. I have explained you everything from top to the bottom on this sheet. Is there anything which is not clear? Please ask. Okay. So let's go back to the problem that we are about to go through. Okay, so let's see this problem. So we have a refrigeration cycle. First of all, it's very clear. This is a refrigeration cycle. It removes 18,000 kilojoule per hour of heat from the cold space. So that will be QL, because it removes this much amount of heat from the cold space. Maintained at negative 30 degrees centigrade. So negative 30 degrees centigrade will be TL. To the surrounding is at a temperature of 20 degrees centigrade, so that will be TH. The coefficient of performance of the refrigerator is 25% of that of the reversible refrigeration cycle. So here COP is equals to 25%, so I will write here 0.25 of this reversible refrigeration cycle. That means COP reversible. Okay. So now we need to find out what is the COP of the refrigerator, determine the power input of the refrigerator in kilowatts. Let's see the solution. The first thing is we need to draw the diagram. Okay, so draw the diagram here, okay, of the refrigerator. Show where is the working, show where is the input, where is the low temperature reservoir, where is the high temperature reservoir. High temperature reservoir is the surrounding. This is the cold space. What is the temperature here? Temperature TH is not mentioned, but you should also mention this. QH, where is the amount? Where is QH? Where is QL? Okay, where is the output? Everything. You need to show everything here. And then once you are done with it, write down all the inputs. Okay, so we have COP refrigerator equals to 25% of COP reversible refrigerator. For reversible, you just need temperatures, okay, TL and TH. So if you know TL and TH, you can find out what is the COP reversible reversible refrigerator. Then after that, once you know this thing, then you can find out the COP of your actual refrigerator. Then use this COP of the actual refrigerator, and you know what is QL, so you can find out what is working, and then this is all what was needed. So is there anything within the solution of this problem which is not clear? Please ask. Everything is okay so far or not?
Yes, sir, it's fine. We understand.
Okay. This is another problem, heat engine with a thermal. You go through it yourself. Again, I have done the solution here. You can just go through it. It's a simple problem. There's nothing in it. Here it is a heat engine. Okay. Carnot corollaries. Carnot corollaries are basically what corollaries is basically what from the statements of the Carnot cycle, from the statements of the second law of thermodynamics, there are some there are some additional outcomes of these. Okay, so these additional outcomes could be represented here in terms of these statements for heat engines and for refrigerators and heat pumps. Anyways, these are just, you can go through it yourself. There's nothing more to it. Temperature scale, as I told you, that the second law of thermodynamics, when we were actually trying to, when the scientists were actually trying to figure out a way to find out the efficiency and then to find out the reference point, and from there they came out with the Carnot efficiency. Okay, so from here this becomes the basis to develop the third law of thermodynamics. But anyways, third law of thermodynamics is something that we are not going to focus on, and it's really not our area of concern here. So the temperature scale was actually developed from this, from the third law of thermodynamics. Okay, so again, this is something, this is a topic you can go through it yourself from the book. This is not of much of our concern here right now in the lecture. Carnot efficiency, I already explained you the basic concept, and then what will be the Carnot efficiency of the heat engine, and then for the refrigerator and the heat pump. Okay, then we have this problem here. Again, this is a simple problem. Go through it yourself. Okay, Carnot cycle. We're gonna go. We're gonna look at it in the end. Okay. There are a few other problems. Okay, I'm going to look here at the most difficult problem. The most difficult problem of this chapter is this one. Okay, so if you understand this one, all of the problems are like easy, no issues in that. Okay, so we have a Carnot heat engine. So remember, whenever you are reading a problem, read the problem very, very carefully. Okay, so each and every word within the problem statement is important. Okay, so we have a Carnot heat engine. Carnot heat engine means, what does Carnot mean? It means ideal, it means reversible, it means maximum. Okay, so you need to have convert all the Q to T values, and then you get the efficiency formulas. Okay, so just the Carnot word give you all these things. These things should pop up in your mind. Okay, so a Carnot heat engine. So we are not talking about heat pump, we are not talking about refrigerator, we are talking about the heat engine. So we have a Carnot heat engine which receives heat from a reservoir at 900 degrees centigrade. So obviously this will be my TH at a rate of 800 kilojoule per minute. So this will be my QH, and rejects the waste heat to the ambient air at 27 degrees centigrade. So this should be my TL, because this is a heat rejection. The entire work output of the heat engine is used to drive a refrigerator. Now you see here two things are connected. So this was the heat engine. These were all the values from the heat engine. And whatever the work output here for the heat engine, so whatever the work output here from the heat engine, this work output behaves as work input for refrigerator. Okay, so the entire work output of the heat engine is used to drive a refrigerator that removes heat from the refrigerated space at -5 degrees centigrade. So this is the amount of heat removed from refrigerated space. So probably this should be my TL for refrigerator. That was the TL for the heat engine. And transfer it to the same ambient air, 27 degrees centigrade. So the refrigerator is taking heat from the refrigerated space and then throwing it into the ambient air. Okay, so this ambient air for the refrigerator behaves as TH for me. Now, point to note is that the same ambient air, when it is used in the heat engine, so in the heat engine, the same ambient air is behaving as TL, And the same ambient air, when it is used for refrigerator, is behaving as TH for me, okay, for this system. Determine the maximum rate of heat removal from the refrigerated space. That will be QL, okay, QL of refrigerator. This is what we need to find. And the total heat of heat rejection to the ambient air. Remember, the heat engine is also rejecting heat to the ambient air. Okay, so we need to get QL for the heat engine. And the refrigerator is also rejecting heat to the ambient air. So that will be QH. So that will be QH for the refrigerator. So these two things, we have to add this with this. So that will be the total heat rejection to the ambient air. And this is the refrigeration effect produced. So this is the problem statement. Now let's have a look at the solution. First, we need to look at the picture. The picture will be very important here. Okay. So you see here, first we have a Carnot engine, Carnot heat engine. For the Carnot heat engine, we have, this is our heat engine. Okay, this heat engine takes the heat from the hot reservoir, the temperature is given, and the heat is rejected to the cold reservoir. The cold reservoir is the ambient air, and the temperature of the ambient air is given. Okay, then QH is the amount of heat which is going to go to the heat engine. QL will be the amount of heat which will be rejected to the ambient air. Work output will be produced. This work output behaves as the work input for the case of refrigerator. Okay, now we have a refrigerator here. For the refrigerator, we have refrigerated space, temperature is given, TL, and this heat goes from the cold reservoir to the refrigerator, and then from the refrigerator to the ambient air. Now here the ambient air behaves as QH, as STH, as the hot reservoir for us, for the case of refrigerator. Okay, so this will be QH, this will be QL for the refrigerator, and W in for the refrigerator will be the same as W out for the heat engine. Okay. So one, we need to find out that how much is the cooling produced. So the cooling will be produced at the refrigerated space, so that will be QL. This is what we need to find. And what is the total amount of heat rejected? The total amount of heat rejected is by the heat rejected by the refrigerator as well as the heat rejected by the heat engine. Before moving towards the solution of the problem, do you understand this figure?
Yes.
Okay. So we're going to move step by step. We know what is the Carnot engine. We know TH, TL for the Carnot engine. We know QH for the Carnot heat engine. For the refrigerator, we know what is TL and TH. Okay. So the first thing is that since we know TL and TH for the heat engine, so we can find what is the efficiency of the heat engine, reversible. It's output over input, so TH minus TL over TH. To substitute the values, you're going to get the efficiency of the heat engine. Once you have the efficiency of the heat engine, and you already know what is QH, okay, so you can find out what is the work output. So that will be the work output for the Carnot heat engine. But we know that the work output for the Carnot heat engine is the work input for the case of refrigerator. So we're going to say here that work out of the heat engine is the same as the work input of the refrigerator, which will be the same value. So now we know what is the work out, we know what is the work in of refrigerator. COP of the refrigerator we can find, because again, these are the Carnot efficiencies we are talking about. So we know TL and TH for the refrigerator. So we can find what is the COP for the refrigerator. So if you know COP and if you know work in for the refrigerator, then you can find what is QL. This was one of the things needed for the refrigerator. Okay. Then for finding for finding the other thing, okay, so if you know QL and you know W in, you can find QH. Similarly, if you know W out and you know QH, you can find QL. So here the QL for the heat engine will be added with the QH for the refrigerator. It's going to give us the total amount of heat rejected to the ambient air. So these two things are determined, added together, and so that's the total amount of heat rejected to the ambient air. This is the most difficult question in this chapter. If you understand this question, then all other questions are simple. Now tell me, do you understand the solution of this problem? Is there any step which is not clear?
So it's all clear, yeah.
Okay. Okay, so that's it. I have showed, I have explained you the whole formula page. Then we discuss most difficult formulas, difficult problems. These are some of the problems. Go through it yourself. My handwritten solution is provided to you. Okay. Remember one thing, when I provide you the handwritten solutions, it's going to give you an idea that when I expect, when you give the exam and I expect the exam solution, it should be in the same format, the way I have been writing my own handwritten solutions. Okay, this gives you an idea that what kind of format I am looking forward when I'm receiving your exam papers. Okay, so just one topic left here, which is the Carnot cycle. Let's discuss about this Carnot cycle. The Carnot was the person who came up with this cycle. Actually, what happened is that he devised a cycle based upon 4 processes, and actually all 4 processes are the ideal processes. In reality, none of those processes are possible. So let's discuss about these processes one by one. So for the case of a Carnot cycle, says that the first process 1 to 2, is an isothermal expansion. Let's first discuss about this process, isothermal expansion. Remember, expansion is a process whenever you expand any gas, whenever you expand any fluid, its pressure is going to decrease. And with the decrease in the pressure, there should be a decrease in temperature. Now, what it's saying is that the expansion is taking place, but it is isothermal. Isothermal means the temperature should not change, but the temperature actually in real world, it should change. So what the Carnot is assuming is that while the expansion is taking place, whatever the temperature change is taking place within the system, it is in contact with the surrounding, and all of that amount of energy which is needed to keep the temperature same is actually provided to this gas. Okay, so the expansion takes place, but the change in temperature does not take place, because all of the energy which was needed was actually taken from the outside air. Okay, and so from the surrounding, and so the temperature of the system remains same. This is an ideal condition. In reality, it's not possible. Whenever you are going to expand a gas, there will be decrease in pressure, there will be decrease in temperature, and it's not possible to keep the temperature same. The only way it is possible is that if very quick and very sudden and amount of energy is being provided while the expansion is taking place, so that the temperature of the fluid does not change at all. Ideally, might be possible, but practically not possible. Then the second step from 2 to 3 is adiabatic expansion. It says, okay, now the next step, we do the expansion, but this expansion is done in a way that it does not allow any amount of energy to be transferred between the system and the surrounding. Again, this is not possible. Why? Suppose I have a gas and I'm expanding it. When I'm expanding a gas, the pressure of the gas is going to reduce. When the pressure of the gas is going to reduce, the temperature of the gas is going to reduce. Now the temperature of the system is reducing compared to the surroundings, so there will be temperature difference. The only way that we make adiabatic expansion is we make such a high insulation that it does not allow any amount of heat transfer to take place between the system and the surrounding. Ideally may be possible. Practically, you cannot make an adiabatic system. There will always be some amount of heat transfer between the system and surrounding, because system and surrounding are all connected together by a boundary. Okay, so there will be some amount of heat transfer practically. But anyways, this is he's presuming an ideal system with ideal processes. So adiabatic expansion is also an ideal process. Actually, there are two extreme ends. Whenever you compress a gas or expand a gas, the temperature is going to change. Okay, so whenever there is a change in temperature, now there are two extreme ends. One end is that you're saying that, okay, whatever the change in temperature is there is a 100% heat exchange between the system and the surrounding, so the change in temperature does not occur. This is also not possible. The other way is saying that, okay, we does not allow any amount of heat transfer to take place at all from between the system and the surrounding. This is again not possible. So these are two extreme end things which are both not possible practically. But anyways, he have used these two extreme end things, and in this way, by designing a cycle, he came up with an efficiency. So these are basically the cycle with the processes where there are no irreversibilities, where they are the ideal processes that occurs, and so the efficiency of these kind of cycles, or the output of these kind of cycle will be maximum, and this becomes actually the basis for getting a reference point. So anyways, second process is the adiabatic expansion, where we say that the expansion takes place without allowing any transfer of heat to take place. Practically not possible. Ideally, we can assume it. And then the next two steps are exactly the opposite of the first two steps. Okay, so 3 to 4 we say isothermal compression, and then adiabatic compression. Isothermal compression, we're saying that we are compressing the gas or the fluid, but because of the compression, the pressure will rise, the temperature will rise, but we does not allow the temperature to rise. How we do a quick amount of heat rejection from the system to surroundings, so the system temperature remains same. Again, this is something practically not possible. Ideally, we can assume it. Then the next step is the adiabatic compression. Adiabatic compression is what? We are compressing the gas, so the temperature is going to rise and pressure is going to rise. And so what we are presuming is that because of the change in temperature between system and surrounding, there might be some amount of heat transfer, but we does not allow any heat transfer to take place. But again, this is practically not possible. Whenever there is a temperature difference between the system and surrounding, there will be some amount of heat transfer between them, and practically it's not possible to actually isolate the system completely. So anyways, these are the four processes. When they combine together, they make up a cycle, and the kind of an output we get from this cycle will be the maximum output. You cannot get an output higher than the output you can get from this cycle, because this cycle involves four processes, and all four processes are actually the ideal processes. Practically none of the single process is possible. So anyways, this Carnot cycle behaves as a reference point to get the work output for any other kind of heat engine or any other kind of refrigeration or any other kind of thermodynamic cycles. This thing, you're going to understand it much better based upon some of the videos that I have attached to chapter number 6 as well as chapter number 7. So there are some videos I have attached regarding the Carnot cycle. Okay, so just watch those videos. I searched them from the YouTube, and some things are better understood with animations. So these videos explain things with animations, so it becomes much easier for us to visualize and understand them. But anyways, I tried to give you some understanding of it. Things will become more clear with time eventually. So our lecture at this point is over actually. So we have covered the whole chapter. There are some practice problems, obviously you can go through them. I've already provided the solution of the practice problems to you. Okay, so is there anything within the chapter that you're not able to understand? Please feel free to ask. Everything is okay so far?
It's interesting. Yes,
All there,
yes.
sir. Okay, so that's it for today, and inshallah meet you next week.
So when will you be studying entropy?
Entropy next class, chapter number 7. 6 is already gone. Next week, inshallah, we're going to start entropy, chapter number 7, and after after that, we're going to start with thermodynamic cycles.
Okay. Okay, sir. Allah Hafiz.
Okay, that's it. Allah Hafiz.
Allah Hafiz.
Office.
Allah Hafiz, sir.
No.